So when we are expanding our study of identities to just some more of the general identities that we'll be dealing with, there is one called the sum and difference identity for cosine. We'll eventually learn one for sine and for tangent as well, but this entire section is just over the sum and difference identity for cosine. Now, it's important to notice that the cosine of some angle minus another angle is not simply equal to the cosine of the first angle minus the cosine of the second angle. And let's prove that fact to ourselves. So if we're doing this where A is going to be equal to pi over 2 and B is equal to the angle 0, so we're working in radians around our unit circle, and then let's look at the following. Cosine of A minus B would be the cosine of pi over 2 minus 0. Okay, well, pi over 2 minus 0 is just pi over 2. So we're really just trying to evaluate cosine of pi over 2. And if you look around your unit circle, what is the cosine of pi over 2? 0. Okay, so cosine A minus B is 0. And if we evaluate cosine of A minus cosine B, just to prove that these aren't the same, we would do cosine of pi over 2 minus the cosine of 0. Well, you guys have already answered for me that the cosine of pi over 2 is 0. And what's the cosine of 0? 1. So what is 0 minus 1? Yeah, it's negative 1. So see how these are not the same? We have to develop a different identity or a different formula, essentially, for when we're adding or subtracting cosine values or angles inside a cosine value. So that sum or difference formula is the following. The cosine of A plus or minus B, and be specific how I'm writing this. It is the cosine of A, cosine of B, minus plus, specifically in that order with the minus on top, sine of A, sine of B. Now, some things to notice about this, and this will make more sense when you see all of the sum and difference identities, but things I notice about this is that in this formula, my pencil is not sticking into here to charge, the cosines are next to each other, yes? And the sines are next to each other. Now, why did I write this symbol specifically like this, do you think? You subtract when you are doing the sum. So the sum of cosines, you would actually subtract in the formula. When you do the difference of cosines, which is why the minus is on the bottom in that parentheses, you're actually going to add in the formula. So it's a little bit backwards. It is specifically minus plus, not plus minus. So to help us out with this kinds of problems that I'm going to ask you, I've made this little table here, and my AP Pre-Cal students found this super helpful, so I put it in here for you guys as well. When we are working with these sum and difference formulas in radians, a lot of times it's harder to decide which angles to use because a lot of times they're going to be simplified versions of these angles. So I've written your degree values, I've written your radian values, and I've written the radian values where they all have a common denominator of 12. That will be helpful for us to see the different kinds of numbers we need to use in these problems. So we're going to use the sum and difference identities to find the exact value of each expression without a calculator. Now, cosine of 15 degrees is not something you know from the unit circle. It's not from the hand trick. It would have to be a calculator question unless we do the following. We know that 15 degrees can be made when you take 45 degrees and you subtract 30 degrees, right? 45 minus 30 is 15. So we can use these two angles, 45 degrees and 30 degrees, as A and B in the formula and expand this out to find values I do know from the unit circle. This would become cosine of 45 degrees, cosine of 30 degrees, plus the sine of 45 degrees times the sine of 30 degrees. I'll highlight because I feel like that might be helpful. Here's your first angles. Here's your second angles. See, I've just filled in the formula. Now we're wanting to do this to make values that around the unit circle we know the answer to. What is the cosine of 45 degrees? Square root 2 over 2. Okay. What is the cosine of 30 degrees? Square root 3 over 2. And then we're going to add the sine of 45 degrees, which is also square root 2 over 2, and multiply that by the sine of 30 degrees. What's the sine of 30 degrees? 1 over 2. Now all we have to do is remember some fraction rules at this point. We're done with trig. We're just doing some arithmetic. When you're multiplying fractions, you just do top times top, bottom times bottom. So then we are doing square root 2 times square root 3. Don't think about it too hard. It's just square root 6. Multiply those numbers underneath the square root. 2 times 2 in the bottom would be 4. So I have square root 6 over 4. And then square root 2 times 1 is just square root 2. 2 times 2 is 4. And of course, since these have a common denominator, oh, how nice that is, we can add these two together as one fraction, square root 6 plus square root 2 over 4. That is the exact value of cosine of 50 degrees. We would not be able to solve for the exact value in a calculator because you'd get a decimal. So if you're wanting exact values, you are going to have to use the sum and difference formulas to be able to reduce using radicals instead of just turning to your calculator. Does that make sense? Now we're going to do the same thing in number B, but if you notice, number B is written in radians. And it has a denominator of 12, which is where this table is going to come in handy. Is there some way I can use these values from the table to make 5 pi over 12? I agree. Now, we're not going to use the divide by 12 versions of these because that's backtracking a second. But since you have them written right next to their simplified version, instead of putting 2 pi over 12 plus 3 pi over 12, you're just going to already reduce that to pi over 6 plus pi over 4. Do we see where I got those numbers from? In the table, 2 pi over 12 is here. So that's pi over 6. Those are the same value. This one is just reduced. This one has a denominator of 12. And then this one, 3 pi over 12, look right above it. It's pi over 4. Yes? Okay. So again, this becomes our A angle. This becomes our B angle. And we can fill out our formulas. For cosines, cosine goes first. This is cosine of pi over 6 times the cosine of pi over 4. Do I put a plus or a minus? Minus. Very good. And then sine of pi over 6. Sine of pi over 4. Again, this is just our A angles and our B angles. At this point, again, we look around our unit circle. Cosine of pi over 6. From your unit circle, what is the cosine of pi over 6? Radical 3 over 2. And the cosine of pi over 4? And we're going to subtract sine of pi over 6. What's the sine of pi over 6? 1/2. And then the sine of pi over 4? You'll start to see these numbers are going to repeat a lot. But don't just jump to conclusions because usually that conclusion is wrong. You have square root 6 over 4 minus square root 2 over 4. And when you subtract those into one denominator, it would be square root 6 minus square root 2, what? Over 4. I just said all the wrong numbers. That's a great question. In the formulas, it's always the opposite of what's in, like, combined together. So since we subtracted in letter A, in the formula we're going to add. Since we added in letter B, we're going to subtract in the formula. That's why the symbol, when I wrote it down, I flipped it over with the minus plus instead of plus minus.
Why don't you ever finish this half?
Like actually subtracting those numbers? We can't. I'd have to go into decimal world to subtract square root 6 minus square root 2. Like, you can't do that algebraically. You'd have to go, like, and estimate the number in a calculator. And this question specifically asked for the exact value. So we don't want to round. Yeah, you can multiply radicals that are not the same, but you can't add and subtract radicals that are not the same. That was a good question. Now, of course, the sum and difference formulas can be used both directions. So in part C, it is already expanded into the formula. We're just going to try to reduce it down to something else. So if we notice, this is cosine, cosine, sine, sine. So I know this is going to be some combination of the cosine values. And I'll take the first degree and then the second degree. I just need to know if I'm adding or subtracting these numbers inside of parentheses. But since you see the minus sign in the formula, what should I put right here? Plus sign. Now what is 87 plus 93? Ooh, arithmetic. 180. In my brain, I did 93 plus 7 is 100. That was 80 left. That's 180 degrees. On your unit circle, what is the cosine of 180 degrees? -1. Oh, look at that. We could still evaluate this function by condensing it using the sum and difference identities to something that I know around the unit circle. I don't know the cosine of 87 degrees or the cosine of 93 degrees because those angles are not a part of the unit circle that I know the values of. But when we combine them, we do know that value. That's good, and it's not harder this year. On to the back we go. Another set of identities we haven't really talked about in a while. We've technically talked about this before, I believe in chapter 2. The cofunction identities. So for any angle theta for which the functions are defined, the following identities hold true. Basically, it has to do with the right triangle idea of complementary angles. We know that the sine of 90 degrees minus theta is going to be equal to cosine of theta because they are cofunctions. The cosine of 90 degrees minus theta is going to be equal to the sine of theta because they're cofunctions. Tangent will be equal to cotangent. They are cofunctions. Secant and cosecant are cofunctions. So cosecant of 90 minus theta is secant of theta, and vice versa. And then cotangent of 90 minus theta is equal to tangent of theta. Now we learned this in chapter 2 because we were dealing with triangles, so the cofunctions worked. But we can also use this in this chapter because these identities will help us find values of things in different ways. So we're going to use one value of theta or x that find one value of theta or x that satisfies each of the following. I don't know why it's so hard for me to read today. So we're saying that the cotangent of theta is equal to tangent of 25 degrees. Well, I want to figure out what theta is equal to. So I would like to relate cotangent to tangent. So what I'm going to do is I'm going to rewrite cotangent as its cofunction, which is 90 degrees minus theta inside of a tangent function. And I do this because now that both sides say tangent, I can basically just drop the tangent. Because if those are equal to each other, their arguments must be equal to each other. So 90 minus theta must be equal to 25 degrees. Y'all see how I just like plucked out the arguments, the numbers? Well, if we solve for theta, that means we subtract 90 to both sides, which is negative 65 degrees. If negative theta is negative 65 degrees, what is theta? 65 degrees. Okay, I'm going to let you guys try B and C. B is still in degrees, but notice C is in radians. So you will have to worry about changing these numbers that I'm using to radians before you try the problem. Here's where I'm expecting us to get stuck. Not on B. Did we get 120 degrees for B? Fabulous. But for C, when you use the identities that I've printed on the paper for you, you now notice that you're using degrees in one parentheses and radians in the other. We need them to match. So let's go ahead and change this degrees into the radian version of 90 degrees. What is 90 degrees in radians? Pi over 2. So when we're doing this one, we would need to switch our values into radians, but then the cosecant should be equal to the cosecant. So we know that 3 pi over 4 should be equal to pi over 2 minus x. I changed to x because the problem changed to x. If you kept theta, that's fine. Just know that the variable here is x. And so if we're solving for x, that means I'm going to subtract pi over 2 to both sides. But when I do that on this side, I'm actually going to go ahead and write it with a denominator of 4 so that it has a common denominator. Is that okay with everybody? Okay, 3 pi minus 2 pi is 1 pi over 4. If 1 pi over 4 is equal to negative x, what is x equal to? Negative pi over 4. So working with radians is only a little stickier because you do have to remember fraction rules, but it's really just getting common denominators, and that's an easy one because the common denominator is 4. So these identities also come into play when we're just kind of doing like the section 5.1 and 5.2 problems, where I want you to take one type of equation, one expression, and write it in a different way. So in the example 3, it says write cosine of 180 degrees minus theta as a trigonometric function of theta alone. Now that just means that eventually we're going to have to get rid of anything that has to do with a degree value. We only want to answer with cosine theta, sine theta, tangent theta, something like that. No numbers, no degree values. So in my head, I see that this is the difference of two values, two angles inside of a cosine. So I'm going to expand that using the sum and difference formulas. This would be cosine of 180 times the cosine of theta, plus or minus, which one? Plus, very good, plus the sine of 180 degrees, I guess I should put my degree symbol there, times the sine of theta. That's just the sum and difference identity for cosine. But if we notice, two of these are trig functions with angle measurements in them. What is the cosine of 180 degrees? -1. So we can change that whole first thing to -1. And then what is sine of 180 degrees? 0. Well, anything times 0 is 0, right? And anything times -1 is just the negative version of that anything. So what does all of that simplify down to? Negative cosine of theta, that's it. So we can use now these identities to do problems again, like 5.1 and 5.2. We're just trying to rewrite it and simplify it in terms of maybe one trig function or no angles whatsoever, just theta. One more type of problem you might see, well, two more types of problems you might see, is finding the value of, bless you, two combined angles when you're not given the angles themselves. So this problem is a little bit lengthy, but the itty bitty bits of it are not that hard. We do have to throw it back to like chapters 1 and chapters 2 to understand what they told us. It says that sine of s is 3/5. That's the first piece of information they gave us. They also said that cosine of t is just my angle measurement this time, is -12/13. Both s and t are in quadrant 2. So if they're in quadrant 2, we do need to remember what that means for our different trig functions. Okay, in quadrant 2, sine is positive and everything else is negative. Do y'all remember that? Ooh, throw it back to all of that. Okay, our goal here is to find the cosine of s plus t. But our problem is we don't know the angle s and we don't know the angle t. So let's figure it out. I'm going to make like a little sidebar over here. Okay, and on my sidebar, we're going to find the values of x, y, and r for both the angle s and the angle t. Let's think about what they gave us in this problem. For the red, sine of s equal to 3/5. It says that sine. Is sine x, y, or r? Something divide by something. Y over r. So I know that for s, the y value is 3, the r value is 5. Now we can quickly figure out what x is. Do y'all know what the value? This is a Pythagorean triple, which is why I'm saying it should be quick. It's 4. Now specifically, since this is in quadrant 2, that is a negative x value. I know this because x would have to be negative to come on this side of the y-axis. So I know that this is negative. If you're like, Ms. Quigley, I'm never going to remember how you got that. Here's how I got it. I did the square root of 5 squared minus 3 squared, which would give me 4. And then I just remembered that in this quadrant, it has to be negative. For t, for angle t, it says cosine of t is equal to -12/13. For cosine, what letters did they give us here? X and r. Why did I give the negative to the x and not to the r? Because it's cosine, it's in quadrant 2. Also, your radius will never be negative because it's a distance. Okay? This is also a Pythagorean triple. Do we remember this one? It is 5. If you didn't, again, all you would do is you would do the radius squared minus one of the side lengths squared, square root that. Triple is basically there's really common side lengths for triangles that make right triangles. 3, 4, 5, and then 5, 12, 13 are the most common ones you'll see. There are more. Basically, if you have whole numbers for all of your side lengths, it is a triple. Those are the most common ones. And I just taught that in geometry, so I couldn't help myself but just do the triple in my head. So if you don't remember your triples, just do the math down there for Pythagorean theorem. Okay, now that we know all of these values, we can come in here and think about what the question is actually asking us. We actually want to know the cosine of s plus t. Now, if we expand that using the sum and difference identity, we would have the cosine of s times the cosine of t minus the sine of s times the sine of t. And I know these letters are confusing because s and t makes this look like it's just a plural cosine and a plural sine, but stick with it. Okay, let's figure out what these values actually are. The cosine of s means I'm going to use the sidebar of s and do cosine. Cosine is x divided by r. So I can substitute in -4/5 for that first bit for cosine of s. I'm getting these, I guess I should make this red. Let me go ahead and make it red so you're like, where are you getting these numbers from? From the red numbers, -4/5. Okay, now that we have cosine of s, we need cosine of t. Now cosine of t was given to us in the problem, but we can also get it from our sidebar. The cosine of t is -12/13. And we are going to subtract the sine of s and the sine of t. Again, sine of s was given to us in the problem, but again, it's y/r, which we can get from our sidebar. And sine of t, which is also y/r, is just 5 divided by 13. Do we see where I'm getting all these numbers from? We had to remember those definitions of sine and cosine from way back to add that into this problem. And now it's just arithmetic. Top times top, bottom times bottom when we're doing these fractions. 4 times 12 is 48. 5 times 13 is 65. 3 times 5 is 15. And again, 5 times 13 is 65. So I can see, again, you have a calculator probably at this point. So at any point you wanted to put this in a calculator, you could. But let's say you didn't and you were doing this by hand. You would combine those together, 48 minus 15. And 48 minus 15 is 33 out of 65. So, yes?
Did you have to do the last part? Like, did you have to?
Honestly, if you were using a calculator, you could go straight from here to here.
Okay.
Once you have all numbers that you're multiplying together, if you have a calculator, use it. But I just can't help myself sometimes. Yes?
What unit am I going to find the x, y, r?
I believe it is chapter 2. Yeah, chapter 2. There's all the triangle stuff that we did. So yeah, it's chapter 2. Okay, we'll be seeing a lot of these sidebars in the coming days where we're doing this. And I know I did the triple part really quickly, but it's just Pythagorean theorem for x, y, and r because they do make a triangle. Now let's verify some identities here. This is exactly like the homework that you got on paper for section 5.1. We're going to verify that the following equation is an identity. We can work with one side or the other. I like to start with the more complicated side, and in my opinion, this is the more complicated side. So we can take this and we can expand it, we can do some stuff to it. The problem is I only have an expanded version of cosine. Do we have an expanded version for secant? Like with sum and difference identities? Did I tell you one? No, so we got to start with something else. What if we use the reciprocal identity here? What is secant the reciprocal of? 1 over cosine. So we technically can write this as 1 over the cosine of those same angles, 3 pi over 2 minus x. All I've done is moved that to the bottom since it's the reciprocal. Yeah.
Why didn't you just put 1 over cosine and then multiply next to it?
Say that again, I missed your question.
1 over cosine and then in parentheses 3 pi over 2 minus x. Instead of them all under them.
Oh, I understand. You're saying, why did I not just do this? Well, remember, the stuff in that parentheses is not multiplied by secant. It's inside of secant. This is the argument for here. As if this was written as secant of theta, you wouldn't leave theta up there. You would move theta with the secant, right? Well, this whole thing is theta. So you move the whole thing with the secant. It's the argument. It's not multiplied by secant. That was a good question. Erase. Oh, no. Okay. Now that we have this, we do have a sum and difference formula for cosine. So we can expand this whole thing out using that sum and difference formula. It would be the cosine of 3 pi over 2 times the cosine of x plus the sine of 3 pi over 2 times the sine of x. By the way, in my shorthand to say what steps I did, I'm going to be doing plus or minus for the sum and difference identities. Is that cool with everybody for my reason? I didn't write the word identity behind this guy. Oh, we didn't technically. Remember in the formula, if you were subtracting two angles inside of a cosine, you add them. Yeah. Now, of course, we see that there is cosine of some angles. I know that two of them still have x's in them. We're going to leave that. But this is something we can get out of the unit circle. From my unit circle, what is the cosine of 3 pi over 2? Zero. So it's going to be 0 times cosine of x. And then what is the sine of 3 pi over 2? -1. Now this is all going to simplify down really quickly. 0 times anything is just 0, and -1 times anything is just the negative version of that anything. So this all becomes 1 over negative sine of x. And if we look at our goal is to get this to be written as negative cosecant of x. Can I do that in one step? Yeah, which identity will I use? The reciprocal identity. So with that last step, we now have finished our proof, our verification. So again, these are like the problems we've seen before. We're adding more identities to our toolkit to be able to do these problems. But when you have an actual angle measurement in here, like cosine of 3 pi over 2, just go ahead and change it to its value on the unit circle if we know it, because usually that will simplify a whole bunch of stuff out with zeros and ones, or 1/2 or square root 3 over 2. So those are easy.